All right, here is another circuits question. This one only has capacitors in it. Go ahead and pause and give it a try. All right, now let's work through the solution. Hopefully you've given this a good effort. Not an easy question by any stretch of the imagination. The first thing we have to pull out of this is certain things like this. The capacitance of this, and this guy are all the same. That's super important. The other big takeaway is that we're saying the capacitance of W is equivalent to, the capacitance of all these guys combined. So I don't know, you can write this any way you'd like, but it's almost like saying this. I'm just going to freehand that into whatever, notation that makes sense in your brain. Now, let's go figure out what this really is. We have to add this, kind of follow the rules for adding capacitors. I'm going to do one thing that hopefully you guys are okay with, and that is simply calling capacitor X. I'm going to call it capacitor Z, and I don't really want to call this capacitor Y. I'm going to call it capacitor Z. I'm going to go ahead and do that because they are all the same. It's given in the question. That's helpful because now I'm just dealing with less variables. If you've added capacitors before, then you've definitely seen this. If not, I think you should not watch this video. So adding capacitors in series follows that sort of reciprocal rule, and you end up with this type of equation. The capacitance actually decreases. They sort of interfere with each other almost. That's a simple way to put it. So when you solve that, those two capacitors in series, you actually end up with CZ divided by 2. But then this one is in parallel. So really, this capacitance on the right side is going to be CZ over 2 plus CZ. If I lost you or confused you, you should pause, slow down, and maybe review how to add capacitors, because all I've done is added the two in series and then recognize that once I have this value, I can just straight up add it with this capacitance. The capacitance, sort of the equivalent capacitance of the top red line, can just get added. So this is like my top line and this is like my bottom line. I add them when they're in parallel. From there, I'm going to rewrite this thing that I just erased in the top left corner. So because I know that the total capacitance in the left circuit is equal to the total capacitance on the right circuit, I get to this point where I'm almost done. If you kind of figured out or deduced the answer from here, you may have gotten slightly lucky, or maybe you recognize that we can just quickly rewrite this. QW divided by the voltage across W. I'm using this equation when I do that substitution. Capacitance, its definition is literally the charge on one of the plates divided by the voltage across that capacitor. So I'm going to sort of do the same thing over here, simplifying this to 3 over 2 CZ. I would get 3 over 2. Again, instead of writing CZ, I'm going to write the charge on the plate Z divided by the voltage across that capacitor Z. Now here comes an important realization. The voltage across W would be the voltage of the battery. And I could say the same about Z. If this was a 10-volt battery, this would be a 10-volt drop across W. And similar story over here. The drop across Z would be 10 volts. So believe it or not, these are the same. The voltage across Z and W are the same. I've got a pretty small, nice equation now whereby I can punch in that 36 microcoulombs because that's a given value. And when you plug that 36 microcoulombs in, you will get that QZ is 24 microcoulombs. That leaves only two possibilities, and there's one quick thing I'm going to do to eliminate option D. How can I eliminate option D? It's pretty simple. it's just realizing what I did earlier with this loop rule. If that voltage across Z is most definitely the same as the voltage across the battery, then let's follow the other pathway to go around X and Y, or through the capacitors X and Y. If I follow that pathway, you should sort of remember this even from studying resistors or light bulbs or anything like that, that this voltage drop and this voltage drop will sort of add up to the voltage across the battery, which was 10, or in my hypothetical situation, the voltage drop across X and across Y would be 5 volts each. So it's more like 5 volts plus 5 volts. Going back to this equation, if I have half the voltage drop across X and Y, they're both 5 volts, for example, then they, in order to have the same capacitance as capacitor Z, then I would also, you can just see how this would totally affect the capacitance, but it kind of tells me that I must have half the charge as well. That would mean that having half the voltage and half the charge, I would have the same capacitance. And that is a very important given detail, that they are identical. The capacitance is identical. So I end up with option A.